Good morning, everybody. Nigel Mbaik here at Katif Technologies, one of the customer success managers. First off, I just want to welcome Nikhil Venkat. Nikhil, how's it going?
Good, Nigel. How are you doing?
I'm doing great. I'm doing great. It's definitely been a fun week, Nikhil. Um, Going over some company meetings, but now we're
Yep.
doing ABA.
Now we're doing
So
ABA.
today we're going to be going over some motion in Inventor, and this is something that we get asked for a lot. Is we can do simulation on things that are static, right? You can apply a load to something, and you can see if it breaks or how it reacts to that particular load. Well, what happens if things are moving, right? That kind of complexifies the entire scenario, and we want to be able to kind of analyze what that looks like without actually having to create physical prototypes and actually performing these tests. Because one, that takes a long time, and two, it's sometimes not cost effective, right? You're going to have to go back and redo the design, and that whole cycle is going to take forever. So, not super fun. So Nikhil's going to be going over that today because that's just something that he is super familiar with as one of our simulation experts here on the team. Just keep a note too that Kativ is a ANSYS and Autodesk partner, so we do provide the best solutions for your needs, regardless of what they are. Nikhil, do you have anything else to add before we get started?
No, not really. Just thank you for the introduction.
Yeah, no problem, man.
All right. So thank you all for joining. As Nigel mentioned, we will be talking about, analyzing motion with Inventor Dynamic Simulation today. The title is, I'd say, a little misleading and also a little vague at the same time. So we're actually going through several different stages of what this analyzing motion, quote unquote, looks like. So one of them is, of course, once you assemble parts together, how are they going to work together? Are they just going to be static parts that are sitting in the positions that you've told them to sit in? Or are they actually going to be working and interacting with the parts that surround them and the parts that they're attached to? Um, and if they are, then that's going to be an area where you might want to focus your analysis on. So
And
today,
real quick too, Nikhil, can
sure.
you? I don't know if your screen share is paused or something, but it's broken on the other half of the stream. So if you want to just unshare and share again, we'll see if that
Oh,
fixes it.
okay. Sorry about that.
Or unpause. I don't know if you paused it.
No, I'm going to stop sharing and then start sharing again.
No worries. Sorry for the technical difficulties, everybody. But we'll get this squared away.
Is that better?
It works on here. It was the other side, and there's a little bit of a lag. So I'll let you know in a couple seconds.
Sure.
All right, you can go ahead, Nikhil. You should
Okay.
be good to go.
All right. Sounds good. Thank you. So, um, yeah, as I was saying, this can be, as small as just understanding what that motion piece looks like and how that interaction between parts is going to happen. Or you can build up and build on that little piece of that motion piece by understanding what the loads are. So, for example, um, if you were to run, I don't know, let's say you had a lifting system or lifting mechanism of some sort, if that slide, the lifting slide, if that were going to be, it could take a maximum load of, I don't know, 2,000 pounds, let's say. Uh, it's probably going to be able to take 2,000 pounds once, but then what happens if you keep adding 2,000 pounds over and over and over again after several years, it is going to fail. So you can also take it one step further by understanding what the life cycle or the life of the product is going to be.
Right, how
So
many load cycles this thing can withstand before
exactly,
inevitably
exactly.
breaking?
Yeah. So how many load cycles it can withstand before it actually breaks? So we sh we do have the ability to go all the way from a dummy assembly that actually doesn't move to all the way to what is the product life cycle if you were to actually assign motion to some of these parts. So we'll start there. We'll start with the assembly portion of it, and then we'll build up from there. So today, I'm actually not going to spend time on a PowerPoint, I'll jump straight into the software, and uh, we will kick right off. So give me a moment while I pull that up on the right screen. I have three different screens here. Give me one moment.
Cool. And while Nikhil's doing that, if anyone has any questions during this webinar, definitely feel free to go ahead and type those in. I'll go ahead and address those when we get a chance. And Nikhil, Inventor 21 looks spectacular. You've got the dark mode on.
Yep,
It is
it does.
something that I love.
Absolutely. Yes, I totally love the dark mode. Definitely easier on the eye as well. So those of you that have been, in the Autodesk world for some time and have been following our AVAs, I'm sure this is not the first time you're seeing this assembly. You might notice some parts are missing on here, but this is definitely not the first time you're seeing this. This front loader assembly is really a perfect example of why motion might be necessary, right? This one has so many little small moving components. It's got hydraulic cylinders. It has lifting mechanisms. It's got pin joints. It's got all kinds of things in there. So we're actually spoiled for choice in what sub-assembly and what subcomponent that we want to analyze here. But I'm actually going to focus on this front assembly. Now this can take some time to load, so I do have one loaded and set up already. Okay. So this is the front portion of the assembly, the front chassis. And what you'll notice is that we have a few extra bearings and a few extra things in here that we didn't previously have. So these are just meant to define the friction and things like that. But there are certain set of rules, certain set of guidelines that we want to keep in mind before we start going into dynamic simulation. The biggest one is dynamic simulation will only work with joints and not necessarily with constraints. So when I say a dummy assembly that doesn't quite move or doesn't quite do anything, I mean, if you were to only assemble or only create the assembly using these assembly constraints, then even though you can specify limits in these constraints, you may have seen these limits here. Even though you can specify those limits, even though you're sometimes able to animate them and everything, that does not necessarily mean that the entire behavior of that system, of that joint or mechanism, is being taken into account. And so a joint will actually give you a little more information. At the end of the day, it comes down to being a set of constraints, but it also defines a set of behaviors. It defines, say, what degrees of freedom are open for motion and things like that. So if you were to use joints to make your assembly, then that's the first step to actually being successful with the dynamic simulation. Now, once you've done that, it is also important to use flexible subassemblies with dynamic simulation. Now, what is a flexible subassembly? Flexible subassembly is anything where you have that icon. Let me be a little more specific of what I'm talking about here. It is that particular icon that you see there in that red box. So a flexible, there's two things that you might kind of get confused with. There's difference between a flexible subassembly and an adaptive feature or adaptive part. Adaptive means your overall geometry is changing. If you have something that's unconstrained, then that may be able to change based on some of the other changes that you make. So that's going to be adaptive. While flexible is going to mean the same subassembly can actually take on multiple positions, right? So if you take this hydraulic cylinder here, for example, there could be an open position and a closed position. And you may want to, or you would likely use the same assembly or the same subassembly in multiple assemblies, one assembly may have it open and the other may have it closed. So that's when it's a good idea to make those components flexible. So it also gives it um, it also makes it a little more reusable and a little more robust in that sense. So that's the next thing, right? So within the assembly environment, you need to make sure that your assembly is actually flexible before you can go into the dynamic simulation portion of it. Now, having done all of your due diligence, having made sure that all of your settings are in before you get into the dynamic simulation environment, you also want to make sure that you don't have too many unnecessary parts here. If you'll notice, for instance, none of these holes here, even though it's quite clear that some of them are going to be bolt holes and things like that, none of them have any hardware in them, right? And that is intentional. Um, Whenever we're running a simulation, whether that's an FE8 type simulation or whether you're running a dynamic simulation like this, you tend to want to avoid bolts because bolts can be quite difficult to deal with sometimes, or any kind of hardware really, for that matter. Um, they can be quite difficult to deal with, and they really don't add much to our simulation. So make sure you get rid of all of that as well. Um, don't just hide it, but go ahead and suppress it. And actually, what we have here is a separate level of detail with all of these unnecessary parts suppressed, and that's likely going to be your easiest way to doing this every single time. So just like you might find a lot of these other advanced environments, the dynamic simulation is also under the environments tab. So it's environments, dynamic simulation. And if you don't have this, it's likely an add-on or an add-in that's missing. So just make sure this is on the list. If it's not, let us know. We can definitely help you with that. Okay, so as soon as you open up a dynamic simulation analysis, you'll notice that there's this player that shows up. And what this player does is simply go from point A to point B as you've defined it. So in this case, it's going to run for 1 second, and in 1 second, it's going to go from the 2 points based on the loads and the constraints that we have. Right. So I just want to show you the results real quick before we get into the setup. So I hit play on that. Notice how this front end keeps moving down along with all of the other components that are associated with it. Right? It's not as if just this one joint or these few joints are moving down or moving in any particular direction, but this entire mechanism is moving and working together. Right? Now the nice part is you don't have to put in all that much work inside the dynamic simulation environment if you've already got most of that correct in the assembly environment. So in the assembly environment, if you've gone ahead, created those joints correctly, and everything seems to be working correctly, then you should be okay. In that, as soon as you jump into dynamic simulation, you will have all of your joints translated automatically, and they are now instead of just defined joints, they're now part of your motion simulation. Right? So you can also add additional, external loads and things like that. This particular simulation is still going, so it will not add. It's not going to let me add anything at the moment, but it should have some graphs for us that we can look at. Right? Let me pull that up. Where'd it go? Okay, here it is. So here's what we're seeing. What we're noticing is that after 0.625 seconds, after that point, the direction changes, which is exactly what we saw, but it gets back to its original position a lot quicker than um, it took to actually get to that final position, right? So it went from 0 to its final position in 0.625 seconds, and then all of a sudden went straight back up for the remaining 0.375 seconds, went straight back to the original position, which from from an FEA standpoint, um, it's this little piece of information is important because it allows you to understand what the loading cycle is going to look like, right? So clearly the unloading is happening much quicker, almost twice as quick as the loading cycle in this case. So that's something to keep an eye on. So again, as we keep going through this, by the way, if you look on the left over here, you'll see positions P2 and P1. Those are, of course, the two different positions, P1 being the initial, P2 being the final. But you can look through not just the position. Right now we're looking at position in millimeters versus time. Or rather time, yeah, position versus time. But you can also look at the force. So what does the force look like? Right, what does that force output look like? And you see again, in order to actually bring that back up to P1, right, that force does spike, that force does increase at some point. And again, that happens to be at that 0.625 second mark. Similarly with the moment, we're going to have the exact same kind of result. So that moment will spike at some point, and that point happens to be that same 0.625 seconds. So again, what we're looking at right now is just one single joint, right? We're looking at one single cylindrical joint, joint 2. That's what we're looking at here, which is this particular joint over here, right? So we're focused on this hydraulic cylinder specifically. Now, if you wanted to go back in here and kind of understand a little more or get a little more information about this, you can go ahead and add a trace, right? So that trace will basically take one single point. Let's say we grab, let's say we grab any point over there. If we were to trace that through the journey that it takes, then it's going to show us how that point changes as it goes from P1 to P2, position 1, all the way to position 2, right? So we're also able to trace individual individual points in individual regions. Now the big thing here, and the reason I like this so much, is because you can actually take this and throw it straight into FEA. Now, there are a couple of things that I want to show you here. Let me pull that up. Okay. Exporting to FEA can be quite a, I'd say it's a challenging task, to say the least, because if a component is part of a welded group, then it's not going to be able to export that out into FEA. That export just doesn't support it, right? And when we say FEA, by the way, we are talking about inventor stress analysis and not inventor Nastran, right? So when you say FEA here, we are talking about inventor stress analysis specifically.
Yep. And that's the Inventor simulation that comes with Inventor Professional. So if you do not have the collection, you have access to this. If you have access to the collection, you have access to all of it. So
yep,
it doesn't actually matter.
Okay, so what you will be able to export into FEA is only a subassembly that is, quote, flexible. So in this case, again, you'll notice that we only have one flexible subassembly here. One. Yep, so it's just this one. And even under this single subassembly, we have two other subassemblies, and only one of them is actually flexible. Right? So if you don't have a flexible subassembly, you will not be able to put this into FEA. Why is it part of a welded group here? And I see there's a question in the chat as well. I have invented 2019. I can't find this dynamic simulation. So as Nigel mentioned already, Inventor dynamic simulation should be a part of the collection. If you don't see it, if you don't have it, then go into environments, click on add-ins, and see if you see it on the list. If you don't see it on the list, then you may need to reinstall your Inventor, or
Yeah, you just reinstall the add-ins.
yeah, you'll have to just reinstall the add-ins. Okay, so I went ahead and grabbed a part that was flexible, and right now this particular part is not really load bearing per se. So what it's asking us to do is select faces for these individual revolutions there. So this was meant to revolve around an axis, and it's asking us to select faces for that revolution, for that particular joint. Right, so I'll go ahead and hit OK here. And again, all we did here is select our load-bearing faces. That is all we did in this case. Okay, so once you you've sort of done that, you can then, of course, go and open that particular part up, run an FEA on it. Right, so so those were the parts that we chose, just FYI. Okay, so if you want to open, let's say, that part right there, right, and this should be fairly simple, fairly straightforward to analyze in general. You will be, oops, wrong environment. You will be able to go straight into stress analysis. Oh, and by the way, if you're trying to just open up a new part and look for stress dynamic simulation, you will not find it. It needs to be an assembly. So you have to be inside an assembly environment. Okay. So what we will be able to do is, now again, I've opened this up as a new part, and that's why it's not pulling up directly. But you can simply grab this motion loads analysis, hit OK, and then it'll grab all of those loads that you found out or that you determined from the dynamic simulation portion of it. Right, so it'll simply grab all of those loads. I'm not able to do it at the moment because this is part of a welded group and it doesn't like it. But Let's see. Let me see if I can try that. Environment stress analysis. No. Okay. Yeah. So it's part of a welded group, so it's not letting me do it at the moment. But what it'll do is grab that entire loading profile and put that straight into the inventor stress analysis environment, and that'll let you figure out whether or not this part is going to be strong enough at the end of the day. We can also do that ourselves, of course. Simple way of analyzing this is understanding how this is actually moving and where the stresses are. So if you wanted to, for instance, go back into the dynamic simulation environment, and if we were to look at the output graph, then we'll see that the force that is acting here is 123 odd Newton until that spike puts us at, I'm going to turn off moment, it's throwing it off. So that spike puts us at 15,000, right? So 16,000 Newton. That's a huge number, and we need to make sure that the spike itself is not going to affect it too much. Okay, so real simple. I'll go ahead and fix that. And again, I'm trying to figure out the absolute strength of this member. That's why I'm fixing it. A pin would obviously make it a little stronger because it's not going to be bending as much. So fixing would give us the literal worst case scenario. Okay, so I'll pick that face and I'll use vector components in this one. The load was acting in this direction. So I'll say in the Fy direction minus 16,000. See what that does. Okay. Now, additionally, you will also notice that all of the materials that we have inside the dynamic simulation environment, they all come straight from all the previously defined materials in Inventor. So once again, if you have this set up beforehand, you don't have to do any work on this once you come into the simulation environment. Okay, so we have a constraint, we have a load. This particular assembly or this particular part is just a single part, so we don't have any contacts, of course. And I'll use the standard default mesh. I'm not going to spend too much time running the simple FEA here.
Yeah, and Nikhil, I don't know if people have seen a bunch of our webinars before, but we've done entire webinars on meshing. Mm-hmm. It does get pretty not complicated per se, but there's a lot of things to think about when you're meshing. And if you're not getting the results that you want, it's likely something in the setup. Mm-hmm. And a big part of the setup is actually meshing the components before you actually perform the simulation itself. So if you want more information on that, you can take a look at our YouTube channel. We've got tons of information on how to set all of this stuff up and how to kind of refine those results.
Yep, absolutely. I believe we've done multiple webinars on meshing itself. So yeah, definitely take a look. And I'll pull that up at the end of this particular webinar session. Okay, so turns out that 16,000 was really it was just one little spike, so we're okay. We're well within our allowable limits. So if you go into safety factor, you'll see a safety factor. The majority of this is 15 and up, right? So that's good. Now, we can take this sort of one step further, right? So I'll go ahead and save this. Go into the environments. And go into Inventor Nastran. So now we're in Inventor Nastran, which is, of course, the next level FEA package. If you notice Inventor Stress Analysis, it's got 2 or 3 different capabilities, but Inventor Nastran has a lot more. So you have all of these different analysis types, and you've got in Inventor Stress Analysis, the previous environment, you only got the first 2, right? So Nastran's got a lot more, and we're going to be using Nastran to understand what the life of this particular product is going to be, and we will use fatigue analysis for that. Again, fatigue analysis is another analysis type that we have gone in depth, in detail on. I believe this was fairly recent, so say about 8-9 months to a year ago. So take a look at that. Again, there's quite a bit going on in the background, even with fatigue analysis. So I just want to quickly run through the sort of things that you could expect, right? So first things first, I'm going to bring in my stress analysis study. So we have our force, we have everything set up here. So I have the force over here. I don't have an idealization yet, so I'll have to make one.
Yep, and just while you're doing that, Nikhil, you can go ahead and keep chugging away here, and I'll just explain what you just did. Is Nikhil imported the stress analysis that he had made on the Inventor dynamic simulation side into Nastran, Inventor Nastran. Because you're not leaving the Inventor, I guess, environment, right? You're staying within Canvas. It does work very closely with one another. So if you're really comfortable using the dynamic sim on the Inventor Pro side and you want to take it a little bit further and take a look at some of this fatigue analysis on the Nastran side, you don't have to reset up the entire thing. So Nikhil's constraint of that being fixed and then that negative 16,000 Newton force that was applied, it's already there. So just another cool thing about staying in Canvas and Inventor, as opposed to, I don't know, when I was learning to do some of this FEA stuff, we're using other software as opposed to the modelers, and we would have to export the model, we would have to apply materials, we would have to apply the force, and do that each and every time we change the geometry. In this case, you don't really have to. If the geometry changes on the Inventor side, it carries over into here as well. So just keep that in mind. If the geometry is fairly similar, the amount of faces or the face names and things like that remain the same. It doesn't matter if the diameter is an inch or an inch and a half. Those loads will oftentimes stay applied even if you change the geometry.
Yeah, I mean, unless you delete that surface or that particular area, that geometry, those loads and constraints will be applied.
Yep.
Yeah, no, that's totally right, Nigel. I think staying within Inventor is so much more beneficial, especially when you're making these quick design changes. You can go back and forth real quickly between design and simulation. Okay, so by the way, all I did here was just make these arrows look bigger, just so you can see them. That's literally all I did. Other than that, though, we have our force, we have our constraints. So we've already run this analysis. We know what the safety factor looks like. We know what the stress looks like, etc. What I'll do instead, though, is change the analysis type. Call this life, and we'll use multi-axial fatigue for this. Now there are a few different things to set up here with fatigue. So one of them is actually putting in our data. So again, we have gone into some pretty deep, in-depth studies with fatigue analysis. So definitely feel free to check that out. 1,000. And this data, by the way, this information, everything that I'm putting in right now, you should actually be able to find that on your material data sheet. So if you look for the endurance curve on your material data sheet, you should be able to find that. Okay, looks about right. And what I'll do is, oops. So the reason I mentioned the curve, the load curve earlier, is because we need to define a load curve. We need to define what one cycle of load is going to look like. So what does one loading cycle and what does one unloading cycle look like? So we'll do that here inside the fatigue analysis portion. We'll define a load history. So from what we saw in the dynamic simulation part of it, at time 0, load scale factor is 0. At time 0.625, this is at full load. And at time 1, the load is back to 0. Okay. And what we saw previously, the curve may have been different, but that was a position curve. Now we're just talking about the force itself, right? So the force increases rather than decreasing the other in the position curve that we saw. So we're just going to say, we're going to try and figure out how many seconds this particular part is going to last for. Again, there is a conversion factor. Oops, that we have here. Okay, there we go. There's a conversion factor that we have, and hopefully that will give us some better results than just telling us that everything's safe. So that's all you need to do, by the way. You just need to make sure that your force, your load, has some kind of history, so it's got some kind of curve associated with it, and you need to make sure that your material model is correct. Other than that, you can go ahead and run the analysis, and it should solve pretty quickly. There we go. All right, so this particular part, again, we should have expected this, but this particular part is what is called an infinite life part, which means it is never going to be the first to be replaced, and let me put it this way, it will never have to be replaced before the overall machine is replaced. So it's one of those parts where, kind of like a bolt or a washer or something like that sort, you never need to replace it. It's useful, it's essential, but you never really need to replace it. So that's what it's telling us here, right? So this is part of that infinite life region.
Yeah, as opposed to the contrary, right? Where if, say, for example, you got you got like, say, 250,000 cycles, right? And the expected use of something is like, say, 500 cycles a day,
mm-hmm.
right? You're looking at like 500 days. You're going to want to have to replace that part before that
yep.
Time to avoid, failures within the assembly. And sometimes that's a lot more catastrophic than others.
Exactly.
So it's really good to know and understand whether or not, like, for example, this thing is infinite life, theoretically infinite, right? So as long as you're applying the correct load to this that you had simulated here, like Nikhil said, you're not going to have to replace this part for the entire longevity of that particular machine, given that, outside things don't occur. So things like rust and things along that will affect this.
Yep, absolutely. So for instance, if you were looking at, say, this arm, for example, then yeah, maybe I'll be a little more concerned if it said you wouldn't need to replace that, because that's one of those things that is going to be quite stressed, and you will start to see some failure around the outer edges
Yeah,
here.
and there's probably subject, depending on how tight everything is, it might be subject to a moment even.
Hmm.
And at that point, you know, some of these simulation things might not be 100% real life.
Yep.
So just keep things like that in mind as well. When we're looking at steel, generally not a huge thing, but especially when you're dealing with things like polymers and stuff,
Hmm.
um, the life expectancy of those, especially when they're under you know, cyclical loading that is pretty significant, right, close to kind of the yield strength of the material. You're going to want to keep that in mind, because fatigue on things that are polymers, for example, they're going to act a lot differently than some of these metals.
Yep. Yep. Definitely. So one other thing that you kind of need to keep in mind is we have simplified this particular analysis so much, right? We're literally only considering the load. In reality, there's a lot more acting on it, where there's friction, there's residual stresses. We considered the force to go from 0 to 16,000. That is in fact not true. If you look at the plot here, the output grapher, you'll see that when we're looking at the force, just the force itself, the resting force is 123 pascals, 123 Newton, which is very, very small, granted, but it's still not zero. So there's there are a lot of different assumptions that we made throughout this process, but the idea is to show you that there is this entire workflow that exists within Inventor and the collection. Now, there is a question here in the chat that I see. It says, which collection? The collection we're talking about is the product design and manufacturing collection. Um,
Yep, and if you're confused as to whether or not you have that or access to that or not, let us know. We can go ahead and look that up for you,
yep.
given your account name and stuff like that. So we can go ahead and take a look to see if you have access to everything that we were showing today. But like Nikhil had said too, um, simulation is a huge piece of product design that, in our experience, has saved people a ton of time by getting to market, right? So imagine you had like, and let's just simplify this, for example, right? Even if we're not working on this like front loader, if we're working on like consumer products, for example, um, and we don't have to make 10 physical prototypes to do the actual testing on it. And those prototypes say they have to be like additively manufactured, right? They have to be 3D printed, and it takes like a day and a half or 2 or 3 days to do these prints, and then another day to make the design changes and so on and so forth, right? If you're going through 10, 15 iterations of a design and you have to physically prototype each and every one, even if that takes a day, right? You're looking at like 3 work weeks, as opposed to something like this where Nikhil could easily change something in the geometry here and just rerun the simulation, right? And that takes a very small fraction of the time. You have to create those physical prototypes. You're utilizing one person, maybe two people's time to do it, and it just saves a bunch on the back end.
Yep. Absolutely, totally agree, Nigel. So before we jump, we go off topic here a little bit. I did want to share that you guys all have access to this. This is our YouTube channel. So some of the things that I referenced today, I may have skipped over them a little bit because there are much more in-depth webinars in here on those exact same topics, right?
Yep.
So we encourage you to take a look at that. An hour isn't really long enough to go through all of these topics in depth. So we encourage you to take a look at, some of these, for example, thermal analysis, or there should also be a fatigue analysis in here somewhere. But just look for KETIV AVA or look for KETIV in YouTube, and it should direct you here, and you'll find a whole bunch of useful webinars. And even if it's not dynamic simulation or simulation, I'm sure you'll stumble upon a whole bunch of things that you find interesting here. So
Absolutely. And this is AVA has been one of the, if not the, longest running webinar series for Autodesk products, right? And so we've been doing this for almost 5 years now. Me personally, I've been on here for pretty much the entire life of my history here at Cative, doing these AVAs. So there are hundreds, if not thousands of videos up now. From the AVA standpoint, it's probably like 250-ish videos, right? We do these every week for the last 5 years. You can imagine that library of videos is immense, right? And we always get requests for doing topic A, topic B, topic C. More often than not, those requests have been made by somebody else sometime in the past, and those videos already exist. So this is a really good place to check. And if you don't see it for some reason, let me know. And we want to make these AVAs driven by the user base. And so if you are someone who wants to see something in particular, let us know. If we can accommodate doing that AVA, we're certainly happy to do so. If it's not kind of fitting within the AVA environment or the AVA, I guess, spectrum of topics, let us know anyways, and we can see if we can go ahead and spend some time with you individually and show you some of the things that you're looking for.
absolutely. All right, so that is all I had. Any questions on this particular topic?
So Dynamic Sim 2, Nikhil, this real quick question that came through.
Yep.
Is it available in like all years of Inventor, or do you have to have a newer one?
No, I believe it's available in all years. As
Going
far as
back,
like going
yeah,
back, say
a reasonable amount of time.
7-8 years. Yeah, 7-8 releases. Yeah, for sure.
Absolutely, yeah. And just to make sure that environment's turned on, go ahead and check your add-ins and stuff.
Yep.
Might not be enabled from that
Oops.
end. Looks like we got a question here from Alexander. Is it possible to trace the center of gravity point of the mechanism in Dynamic Sim?
So, yes, but I don't think you need Dynamic Sim for that.
Yeah, you can pull the CG from the physical properties, right?
Exactly. You should just be able to pull that. That's going to be a physical property. It's going to be based on the mass anyway. So that should not have anything to do with Dynamic Sim. If you're talking about a moving CG, depending on how the simulation moves, then no, that would not be possible.
Yeah, at that point, I would create different view representations of the assembly and then look at the physical properties each time, or positional reps, not
positional reps.
Yeah, and it should pull it. So Alexander, if you have issues and need some help with that, let us know. We're more than happy to do that. Brian Kelly, shout out to you. Thanks again for joining. You've been here so long, and congratulations on the position. Definitely.
Yeah, congratulations, Brian.
All right, let's take a look here. I'll give everyone another 30 seconds or so to ask any more questions that they do have while making a couple of announcements. Like I said, we went through a simulation AVA today. Some of the people on here may be interested in more advanced simulation or maybe have some requirements for more advanced simulation. And if you didn't already know, I mentioned this at the top of the broadcast as well, is in addition to being an Autodesk partner, we're also a partner to Ansys, which if you haven't heard is the leading firm for design simulation, right? And so we have solutions from your basic static stress simulation all the way into multiphysics, right? And so whatever your needs are, let us know. We'll find a solution for you. There's also an AVA series directly for Ansys. Instead of Autodesk Virtual Academy, it's Ansys Virtual Academy, also brought to you by your friends here at Cative Technologies. I don't host those, somebody else does on the Ansys side, but definitely want to share that information with you. So if you go to the Cative website, you'll find signups for the Ansys Virtual Academy there as well, if you're interested in something like that. It looks like we don't have any more questions, but if anyone has anything else to add, definitely feel free to reach out to myself or Nikhil or anyone here on the Cative team. We'll go ahead and answer those questions for you. Looking forward to everyone joining us for AVAs in the future. Stay tuned. Next week, we're going to be going over some BIM stuff, some building information modeling information for manufacturing specifically. So maybe if you're not in the construction space, but you're building things that go in construction space, which is a lot of manufacturers, definitely something you should be interested in joining. So thanks all, everybody, and we'll see you next time. Thanks again, Nikhil, for joining us.
Thank you all.